This is ACT Manual, ACT Math Manual, Section 10. Section 10 deals with exponents. This starts on page 71. Before we get into this section, I do just want to make a note that most of what we go over here will be review. It will not necessarily be going into the depths of exponents and why the exponent rules are the way they are. We will generally just be going over the rules themselves, not discussing the basis for the rules or the derivation for the rules. So if you are interested in knowing why these things work the way they work, you're going to have to talk to your tutor or do a little bit of research on your own. So let's get into this. Before we start doing the actual rules themselves, let's talk about some terminology. So in this term here, we actually have a few things that we need to know the names of. The 3 is known as, anybody? Class? Anyone? It is known as a coefficient. The x, a lot of students will say the x, oh, that's a variable. And yes, you're right, x is a variable. However, when we're talking about exponents, we do need to note that that x, while it is a variable, it is also the base. It is also the base of the exponent. All of this stuff is going to be important when we actually start to do the rules. We'll need to, again, be familiar with this terminology. And then the 2 is the exponent, or the power, it may also be referred to. Now over here on the right, this 4, a lot of students may immediately think that because the 4 is a numeric value, and that's like the 3 over here, which is also a numeric value, students might say that this 4 is a coefficient. But again, keep in mind what we just made mention of, and that is that the item under the exponent is always known as the base. So this 4 is not a coefficient. If there were, let's say, a 3 out here in front of this 4 to the 5th, then this 3 would be a coefficient, sure. But in this case, the 4, which is underneath the power or the exponent, I'm going to write that down. The 4 is our base in this example. So you do have to keep in mind that you can have variable bases or you can have numeric bases. And the rules will apply equally to those scenarios. Now, you do have to make sure you are 100% confident with these exponent rules that we're about to go over. There are questions on the ACT, on almost every single ACT, that test very straightforwardly these rules. In fact, an example like number 1, it's not uncommon to see a question like this on the ACT. That's why we use these examples, because they look like ACT questions. But either way, ACT could come right out and give you something like this. And if you are not sure of your exponent rules, you are going to run the risk of making a careless mistake. So what we do when the terms have common bases, when we are multiplying two terms that have common bases, in other words, when we have, I don't know, let's say a square up here and a cube up here. When these two things are the same, what we do is we add the exponents together, and if there are any coefficients, we multiply them. So in this example here, same, by the way, if you want to just run through examples 1 through 16 in the left-hand column, in the example column, you might want to hold off on the common mistakes to avoid, because a lot of students are unsure of what the mistakes are because they wouldn't make those mistakes. So if you want to do this first column on your own and then come back and check your answers against what I come up with, you can definitely do that. Just pause the video and do so. So what we do in example 1 is we multiply the coefficients, we get 15, we add the exponents, and we would get 10. Down here in number 2, we have bases of 2 and different exponents. So remember, all we do is we add the exponents and multiply coefficients. There are no coefficients here. Remember what I said before, this 2 is not a coefficient, it is a base. So we don't change that base, we simply add the exponent. So we get 2 to the 8th. In number 3, we do 2 times -4, those are the coefficients, so we get -8. Then the x terms are here and here. We add the exponents. Remember, there is an unwritten 1 on this x over here when we just have a variable or a number. So a variable like y or a number like 3. Remember, there is an unwritten exponent of 1 on those terms. The convention is simply not to write the 1. So we have x squared times x to the first. That would give us x cubed. Then we have a y cubed times y to the fourth. Remember, we just add the exponents. That would be y to the 7th. And then there's just a z to the 1 here. There is no z term over here, so we just keep that as z. Anyway, that would be examples 1 through 3. Now I am going to jump over here to the common mistakes to avoid. Be careful of multiplying your exponents. Do not do that. That is a common careless mistake that's not going to get you any points, unfortunately. X squared times x cubed would just be x to the 5th because you're supposed to add those exponents. Be careful of multiplying your numeric bases. Some students will say that 4 squared times 4 squared is 16 to the 4th. No, it is not. These bases do not change. We do not multiply these bases together. This would just be 4 to the 4th. Here, you have to be careful of not multiplying terms that have different bases. For instance, this would not be something like AB to the 5th or even AB to the 6th. Those would both be common careless mistakes that students make. This a cubed times b squared would literally just be a cubed b squared. There's nothing more you can do with those terms. In terms of division, again, the terms have to have common bases. They have to have the same base. And if they do, you subtract the exponents. Remember, up here in multiplication, we were adding exponents. In division, we're subtracting exponents and we're dividing the coefficients. So in example 7, remember, there are no coefficients here. These 6's are bases. So we don't do anything to the bases. The base remains the same. And we get 6 to the 9th because I just subtract the two exponents from each other. 12 minus 3 is 9. At least it was yesterday. I'm not sure if they've changed it. Then in example 8, we do have some coefficients here. We have the 36 and the 9. So we divide coefficients, we get 4, and then we subtract the exponents. So that's going to be 4y to the 4th. Over here, things that you have to be careful not to do. Be careful of dividing your exponents. So x to the 16th over x to the 4th would not equal x to the 4th. It would equal x to the 12th. 16 minus 4 is 12. We do not do 16 divided by 4. Also, be careful, similar to the careless mistake we discussed in number 5, you have to be careful not to divide numeric bases. So we have numeric bases here. The 7 is the base. We do not divide those bases. We simply keep the base the same and we subtract the exponents. So sorry, let me write the incorrect thing here. The incorrect thing would be something like 1 squared. Again, that would come from a student dividing the bases. The correct thing would be 7 squared, where we simply subtract the exponents. So that is division. Now, in terms of dealing with parentheses in exponent questions, the rule that you need to know is that you have to multiply every exponent that is inside the parentheses by the outside parentheses. So again, if you see an exponent inside and an exponent outside, those two numbers are being multiplied. You also need to, and this is something that students forget to do, it's a common cause of careless mistakes. I'm going to go ahead and highlight this. You need to make sure that you raise any coefficient to the outside exponent. We'll see an example of that in 1 second. So in example 11, again, there's no coefficient here. This 3 is a base, as I've been saying several times. So we do 3 squared, and then outside parentheses we have this 4th. So we just multiply these two numbers, the 2 and the 4, and we get 3 to the 8th. So 3 to the 8th is the correct answer there. I'm going to zoom in here a little bit. Now in example 12, again, inside exponent we multiply by outside exponent, but we also have to raise any coefficient, and here we do have a coefficient. We need to raise that coefficient to the outside power. So this would be 6 cubed t to the sixth. So the sixth comes again from multiplying these two numbers, and we have raised our coefficient to the third. This, I believe, would come out to 216 t to the sixth. You can check 6 cubed in the calculator if you don't believe me. And if you don't believe me, well then, forget you. Now, number 13, so now we have these three terms inside the parentheses, but the rule is no different. We are simply going to multiply all inside exponents by outside exponent. So it would be x to the 10th, that's the 2 times 5. It would be y to the 5th, that's the 1 times 5. And z to the 15th, that's the 3 times 5. Now, in terms of adding and subtracting terms, so first things first, most important point, you need to make sure that when you are trying to add and subtract terms that you're dealing with like terms. Like terms are terms that have the same base and the same exponent. Same base, same exponent. If you do not have the same base and same exponent, you cannot combine terms in the way that we are about to combine terms. So if you have like terms, you simply do what it says here. You add and subtract the coefficients. So in example 14, do we have like terms? Yes, we do. We have a base of r, exponent of 2, base of r, exponent of 2. These are like terms. Keep in mind that when we just have an r squared bare like that, there is an unwritten coefficient of 1 in front of the r squared. So this is 1r squared minus 5r squareds. So if you take 5 r squareds away from 1r squared, you are left with negative 4r squareds. Your 4r squareds in the whole. Now, number 15, very, very common on the ACT, is this idea of distributing a negative. I always make sure that I draw my distribution arrows from the negative outside to the terms on the inside so that I remember to distribute the negative to the two terms. So this would be 3n squared minus x, that's negative 1 times x, that's those two guys, minus 5n squared. So that's the negative 1 on the outside times the positive 5n squared gives me negative 5n squared. And now I have like terms. I have base of n exponent of 2, base of n exponent of 2. So I can actually take away these 5n squareds from these 3n squareds, and I'm left with negative 2n squared minus x. Number 16, again, same base, same exponent. So all I do is I add these coefficients, and the easiest way to do that, yes, you could find a common denominator, but that requires some brain power, and I don't want to waste any brain power right here, so I'm just going to do 1 divided by 2, and I'm going to add that to 1 divided by 4, and I'm going to use my trusty, so it's 0.75, I could just write the decimal, but I'm going to use my trusty math enter sequence to convert this to a fraction, and I'm going to write 3/4 b cubed. 3/4 b cubed. Now over here on the right hand side, common mistakes to avoid when we are adding and subtracting terms. You have to make sure that if you do not have the same base and the same exponent, same base, same exponent, which we do not have here. We do not have the same exponent. If that happens, you cannot add or subtract your terms. So do not make the mistake of thinking that this is, let's say, 5x. In other words, subtracting the coefficients and then maybe subtracting the exponents. That is not correct. You could do something here. You could actually factor. You could factor out a 5x squared, and you would be left with 2x minus 1 in parentheses. So you could clean this up a little bit if you consider factoring cleaning up, but you certainly cannot simply add and subtract these terms. S squared plus s squared. Do not make the mistake of thinking that this is s to the 4th. This is not s to the 4th. We do not, remember, for instance, when we did example 14, we didn't get negative 4r to the 0. In other words, we did not subtract these two exponents. All we did is we subtracted the coefficients. Well, this s squared and this s squared, they do have coefficients. They have a coefficient, again, of 1. Remember, when no coefficient is written, the coefficient is 1. So this is not s to the fourth. We do not add the exponents. All we do is we add the coefficients, and we get 2s squared. Down here, we have to make sure we don't do, there's actually a couple things we have to make sure we don't do. We have to make sure we don't do 9 to the x. In other words, we do not add the bases. We have to make sure we don't do something like 3 to the 3x. In other words, we don't add the exponents. Remember, we only add exponents when we are multiplying terms. And I guess we also have to make sure we don't do 9 to the 3x. So none of those are correct. There is a way to simplify 3 to the x plus 3 to the x plus 3 to the x. And if you're interested to know how, you can always ask your tutor. Typical, so this is the next page, page 72, very typical type of basic exponent question, number 8. So they want to know what this product is equivalent to. Keep in mind, if you were struggling on your exponent rules, if you were really unsure of them, or you had forgotten them and you were worried that you weren't going to get this right, or you're going to make a careless mistake, you could use Vita here. It's not going to be that tin technique, Vita, is not going to be as efficient as doing this with the regular old memorized exponent rules, but you could save yourself the points by plugging in some numbers for x and y and using your calculator, since you're going to get quite big values here. So I'm going to go ahead and do this the quote-unquote correct way, or school way. 3y to the 8th. So again, remember what we do here. We multiply the coefficients, we get 6. The x terms, when we multiply them, so they have the same base but different exponents, remember that we add the exponents when we're multiplying, so that will be x to the 9th. And then this y and this y to the 8th, remember this is a y to the 1, so y to the 1 times y to the 8th is y to the 9th. So this should be 6x to the 9th, y to the 9th. Is that what they were asking? Yes, they were asking what this product is equivalent to. So we get answer choice H. Now, moving into some advanced exponent rules. These are a little bit trickier, a little bit tougher. These tend to be the things that ACT uses to spice up certain exponent questions. So again, we're going to mostly be just reviewing here. If you are shaky on any of these, you got to do a little bit of extra work. Negatives and even odd exponents, even or odd exponents. So remember, when you have a negative and you raise that negative to an even power, what you're doing is you're multiplying that thing, well, in this case, you're multiplying that thing by itself twice. But even if this were, let's say, a 4, you would be multiplying it by itself 4 times. And what would end up happening when you have an even exponent is negative times negative, negative times negative, you end up with positives. So the point here is, and I'm going to get rid of this schmutz here. So the point here is that when we raise a negative to an even power, we end up with a positive result. In example 2, when we raise a negative to an odd power, so remember this is going to be negative 2 times another negative 2. Well, these two negative 2's are going to give us the positive, but then when we do an additional multiplication by negative 2, we're going to be doing a positive times a negative, and we're going to end up with a negative result, in this case negative 8. So point there is that a negative raised to an odd power is always going to remain negative. The trickiest one of the bunch here is example 3. Keep in mind that negative 3 to the 4th is not equivalent to negative 3 to the 4th. In other words, if there are parentheses around the negative 3, what you are doing is you are raising this entire term to the 4th power, which, as we just saw in example 1, would turn this positive. But if we're just doing a negative, a 3, and a 4th, we have to follow order of operations. And order of operations says we do exponent first, so we take the 3 and we raise it to the 4th, and then we apply this negative 1, which is basically, as I just said, a negative 1 in front of this 3 to the 4th term. So negative 3 to the 4th just so you can see this written out, is like -1 times 3 to the 4th. You do, by order of operations, the exponent first and then the multiplication. PEMDAS. Exponent first, then the multiplication. So -3 to the 4th with no parentheses around the -3 will be 3 to the 4th, which is 81, and then we multiply by the negative. So this would remain negative. So these two rules down below these examples illustrate what happens really when you're doing examples like examples 1 and 2. In other words, when the negative is in parentheses. So a negative number raised to an even exponent becomes positive, and a negative number raised to an odd exponent stays negative. Very, very tricky concept, especially you have to be very careful when you're using your calculator. You have to know which situation you're dealing with, whether it's this situation or this situation, and that might take a little bit of practice or a few careless mistakes before you learn your lesson. Fractions and decimals and exponents. So we need to know generally what happens when we take a fraction between 0 and 1 and we raise that fraction to an exponent greater than 1. What happens is, so 1/4 squared, I can either do this in the calculator or think of this as 1/4 times 1/4, or I could even think of it as 1 squared over 4 squared. A lot of different ways we can think about this. Bottom line is it becomes 1/16. And if we if we compare the original fraction that we squared to the resulting fraction, we can see that the result is smaller or lesser than the original fraction. So whenever we take a fraction between 0 and 1 and we raise that fraction to an exponent greater than 1, we're going to get a smaller result. Over here on the right, same sort of thing with decimals between 0 and 1. 0.5 cubed, we are going to do that in the calculator. 0.5 cubed. And look what we get 0.125. So again, we're getting a result that is smaller than was the original decimal. Solving for a squared variable, one of possibly the trickiest types of questions that ACT can ask. Definitely a cause of many, many careless mistakes. So the square root of a number, if I just say that x equals the square root of 16, in mathematics, this is taken to mean the positive square root and only the positive square root of 16. So again, if a question just comes right out and tells you that x is equal to root 16, or they even just give you root 16, they don't say x equals over here, this is taken to mean the positive square root of the number under the radical sign. However, if you are solving for a squared variable, so at some point in the question you are given or get to x squared equals root 16, and then to solve you take the square root of each side, in this case you do have to account for both the positive and negative value. If I take positive 4 and I plug it in for x, 4 squared will be 16. If I take negative 4 and I plug it in for x, it would be this situation. X squared, negative 4 squared, I would also get 16. So two values result when we are solving for a squared variable. Only one value results when we are simply given the square root. It is a little tricky. If you need further clarification, ask your tutor. So squared variable, two solutions. Raising to the 0 power, everybody should know this, hopefully. You get 1 when you raise to the 0 power. So 2 to the 0 would equal 1, x to the 0 would equal 1, y to the 0 would equal 1, so this would equal 2. Any value raised to the 0 power produces a result of 1. 1. Always, always, always. Negative exponents. Some students are very confident with negative exponents, other students very not confident. Depends a little bit on, I guess, on your teacher in math class and on whether you were paying close attention to said teacher. Of course, if the teacher was no good and you were paying attention, that wouldn't have helped much anyway. But so negative exponents, I'm going to teach this in a very sort of memorizational / robotic way. If you have a different way of thinking about negative exponents or dealing with negative exponents that works for you, great. More power to you. You go ahead and do it that way. However, again, to make this as robotic as possible, I am going to go ahead and do this the way that it's laid out here. So if you have a term with a negative exponent, you're just going to move that term. If the term happens to be in the numerator of a fraction, so if the term is in the numerator of the fraction, you take the entire term, both the base and the exponent, and you put it in the denominator, and you make the exponent positive. So your first step again is to put the term into the denominator. Your second step is to make the exponent positive. So x to the negative n is the same as x to the negative n over 1. So notice we have a term with a negative exponent in the numerator of a fraction. We take that term, we put it into the denominator, and we make the exponent positive. So x to the negative n equals 1 over x to the n. Now, if you know about negatives and how negative exponents and how they relate to reciprocals and all sorts of other stuff, like I said, that's great. That's very good. You have hopefully a good understanding of what negative exponents are and what they mean, and might have a little bit of a deeper understanding than what I just did here would require. I am simply giving you this method because, like I said, it is generally the most robotic. Now, if the term is in the denominator, you're doing something similar. You're just moving in the other direction. So if you have 1 over x to the negative n, so notice we have a term with a negative exponent in the denominator. We take that term, we throw it up into, we put it up into the numerator, and we make the exponent positive. So 1 over x to the negative n, x to the negative n goes up into the numerator, exponent becomes positive, and we end up with x to the positive n. So let's take a look at how this would work in example 9. So b to the negative 2, remember that's the same as b to the negative 2 over 1. What do? Since the term is up in the numerator, we take it down into the denominator and we make the exponent positive. So this would simply be 1 over b squared. I've taken the b to the negative 2, I've put it in the denominator, I have made the exponent positive. 3 to the negative 3, same sort of thing. That is a 3 to the negative 3 in the numerator. I take the 3 to the negative 3 term, I put it in the denominator, I make the exponent positive. This would also be equal to 1 over 27. Keep in mind that your calculator will also handle 3 to the negative 3 for you, so that you didn't really have to apply any exponent rule. You could just do 3 to the negative 3, hit enter, maybe math enter that bad boy, and get 1 over 27, which is exactly what we just got. Over here in example 11, obviously this one is the most complex of all of these. So let's start with this first negative term here, this x to the negative 4th. Let me zoom in on this a little bit. So the x to the negative 4th, remember what we do? We take it up into the numerator and we make the exponent positive. So there's now an x to the 4th in the numerator. And this next negative term, or should say negative exponented term, is y to the negative 1. Well, that's up in the numerator. We put it down in the denominator and we make the exponent positive. So this guy is no longer in the denominator. This guy is no longer in the numerator. And what we have is x to the 4th, x squared over yz. Remember, these two terms have same base. When we multiply two terms with the same base, we just add the exponent. So our final answer is x to the 6th over yz. And that is example 11. Now we have some stuff on fractional exponents. In terms of fractional exponents, again, a lot of this is just going to be memorization. You need to understand that when you have a fractional exponent, the number in the numerator of the fractional exponent is your power. It's what you are raising the base to. And the number in the denominator is your root. It is the root that you are taking of the base. And you can actually do this in two different orders. The order doesn't matter. In other words, you can take the base, raise it to the power, the numerator of the fraction, and then take the root of that result, or you can take the root of the base, okay, take the denominator root of the base, and then raise that entire thing to the numerator, the power, so that you can see how this works with an actual number. So 4 to the 3/2. So remember, either order is fine. We can raise 4 to the 3rd power. That would give us 64. And then we can take the second or square root of the result, and that would produce an 8. So that would look like, this. Let's do 4 cubed and there. So that would look like that. Or we could do the reverse order. We'll get the same answer, but we could do the reverse order. We can take the square root of 4, which would be 2, and we can raise that to the 3rd power. What that would look like is this. So again, this is an opportunity for you to do things in whatever the heck order you want. Now keep in mind, one more time, you can use your calculator to handle fractional exponents. You do have to be slightly careful if you have a calculator that will not put, so when I do this in this version of the TI-84, you can see that everything pops up into the exponent and stays in the exponent. So 4 to the 3/2 equals 8. Sometimes, however, on some older model calculators with older operating systems, you have to make sure that you put a parentheses around the entire fractional exponent, or you are not going to get the correct answer. You will need to know your calculator well enough to know whether you need to use the parentheses. Now, how do we clear a fractional exponent? In other words, if I'm given x to the 3/2, how do I isolate x? Well, the way that I isolate x is by applying an exponent rule that we talked about before, and that rule was the rule that dealt with parentheses. So I place the x in parentheses, I'm placing the 8 in parentheses in preparation for what I'm about to do next, which is I'm going to raise each side to the 2/3, which is the reciprocal of 3/2. And why am I doing that? I'm doing that because I'm now going to apply the parentheses rule that we learned before, where if we have an exponent inside and an exponent outside, we multiply them. Remember, 3/2 times 2/3, boom, 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 equals not 0. They don't just go away. It equals 1. That was the whole purpose of raising this term to the reciprocal of this exponent. We did that so that we would end up with an exponent of 1 on the x, which is just x alone, and then 8 to the 2/3 I can just do in the calculator. 8 to the 2/3 would be 4. So the point here is that if you want to clear a fractional exponent in an equation, in other words, if you have a variable that has a fractional exponent and you want to isolate that variable, you just raise both sides to the reciprocal of the fractional exponent, the reciprocal of the fractional exponent. Moving along to page 74. Page 74, we need to talk about common bases. There are some questions on the test where you are going to want to convert all of your bases to a common base. Some students are very proficient at doing this. Some students are either shaky or possibly have never even learned this. So I'm going to go ahead and do example 1 a little bit more thoroughly, perhaps. So what I notice right away is that both of these bases can be written with a base of 2. 4 can be written as 2 squared, and 2 is already in base 2 form. It's 2 to the 1st. So what I'm going to do is I'm going to take this equation, I'm going to rewrite everything with the common base of 2. So 4 to the 2x is the same as 2 squared to the 2x. That's the left-hand side of the equation. Again, I'm just replacing the 4 with base 2 to the exponent 2. Over here, I'm going to keep the base the same. And now I'm going to apply my exponent rule that I've talked about a few times. Inside exponent, I multiply by outside exponent. So I get 2 to the 4x equals 2 to the 1 minus 2x. And now I can drop my bases. Why can I drop my bases? Well, I know that if my bases are the same and these two sides of the equation are equal, these two exponents must be equal. It's the same thing as saying, if I had 2 cubed equals 2 to the x, well, I know my x has to be equal to this 3 over here since my bases are the same. So I can drop my bases away and I get 4x equals 1 minus 2x. I add the 2x. Now we're just doing simple algebra. Add the 2x, I get 6x equals 1, divide by 6, I get x equals 1/6. So by applying common bases there, I was able to determine that the value of x has to be 1/6. I could verify that by throwing 1/6 back in for x and using my calculator to calculate both sides of the equal sign and make sure that they are equal, but they are equal indeed. Now, number 49, let's go ahead. You might, if you feel confident about common bases, you can try 49 on your own. I'm going to go ahead and do it right now. So in the real numbers, what is the solution of the equation 8 to the 2x plus 1 equals 4 to the 1 minus x? So we need the solution to this equation. Again, this is a common base of 2 problem. We are going to replace the base of 8 with 2 cubed, which is what 8 is. So we have 2 cubed to the 2x plus 1. And we're going to replace the base of 4 to the 2 squared, which is 4. So 1 minus x. So again, I've just replaced the base of 8 with 2 cubed and the base of 4 with 2 squared. Now I apply that good old multiplication rule. And I do need to remember to distribute this inside exponent to both the 2x and the 1, and this inside exponent to the 1 and the negative x. So on the left, I'm going to have 2 to the 6x plus 3. On the right, I'm going to have 2 to the 2 minus 2x. Remember, then we can just drop our bases and set the exponents equal to each other, which will give me this equation. And now I've just got a simple algebraic equation to solve. So I get 8x plus 3 equals 2. Subtract the 3, I get 8x equals negative 1. Divide by 8, I get x equals negative 1/8. Let's make sure that's what they were asking. Yes, they were asking for the solution, which is the value of x. So my answer is C. Now, an astute student when it comes to the tin techniques might notice that we have numbers in the answers and they are asking us for the x value, for the solution. So we could have nidused this. We could have taken these answer choices and plugged them up into the value of x to see which answer made both sides of this equation equal to each other. For those of you who have already watched the nidus video or done the nidus section with your tutor, you know about nidus. For those of you that haven't, oh, you are in for a treat. Anyway, so yeah, you could have plugged these answer choices in for the x value. Now, finally, square roots. Square roots, you do have to be aware of a few rules. So look at these examples over here. They're not numbered. These examples pertain to this rule, which says that if you have a root in the numerator and a root in the denominator of a fraction, you actually can combine the two things under the equal sign into the same fraction under a single square root. So root 8 over root 2, we can actually combine those two values under the same square root, and we get root 8 over 2, which is root 4, which I'll skip a step there and just write 2. So again, root 4 equals 2. And then we can also split if we are, so we can go in either direction here. We can go from left to right or right to left. So in this case, we would go from this form on the right to this form on the left. We can split these two items into their own square roots. Why would we do that? Well, we would do that so that we can simply put a 3 in the denominator. Similar thing we can do with multiplying two square roots. We can take the two things under the square roots that we are multiplying and combine them in a single square root. So root 5 times root 20 would be root 100, and that would equal 10. We can also split the two things that are being multiplied under the square root. So we get root 6 times root 9. The root 9 is 3, so this would just be 3 root 6, simplified a little bit. Now, down here at the bottom, you do need to know that when we take one square root and we multiply it by an equivalent square root, we just get the thing under the square root sign. So any square root multiplied by itself gives you the thing under the square root sign. So root 2.3 times root 2.3 would be 2.3. Root happy face times root happy face would equal happy face. It is a rule that you should know. Down at the bottom of page 34, a lot of students look at a question like this and they start thinking, oh crap, I can't remember how to break down square roots, so what the heck am I going to do here? And the very simple answer is, don't fret about a question like this if you don't remember how to break down square roots. You can simply go into your calculator and do square root of 50. Make sure you get out of the square root, add to it square root of 128, square root of 128, and hit enter. You get this 18.38, and then you would just go to the answer choices and do the calculations in your calculator, and you will find that answer choice, I can't even remember what it is. Let's see, 13 times root 2. Oh, that worked out well. The answer is F. So this answer choice equals that 18.38. So you can just use your calculator on a question like this. It's kind of amazing that ACT still even asks questions like this, considering you get to use your calculator. The way that you would do this, the quote-unquote correct way or school way, is you would break down these square roots. And I'm going to do this very quickly. If you are not sure of what I am doing, you're going to need to review this or ask your tutor. So root 50, I can actually write 50 as the product of 25 times 2. Remember what we said up here in these examples. I can actually separate these out into their own square root. So this would be root 25 times root 2. Root 25 is 5. So this is just 5 root 2. And then the root 128, well, 64 goes into 128 2 times. So this would be root 64 times root 2. And then I can split that into root 64 times root 2. And that would be 8 root 2. And now I am adding those. I'm adding, this was root 50. Root 128. So 5 root 2 plus 8 root 2, that's 5 root 2s and 8 root 2s. If I put 5 root 2s together with 8 root 2s, I get 13 root 2s. In other words, I'm just adding the, you could think of these as coefficients here. I'm just adding the coefficients and I do get answer choice F.